You reach up and scratch the back of your neck. Your wrist bends. Your fingers curl. None of it takes any thought at all. It feels like nothing because it is nothing, just another automatic motion in an ordinary day. But underneath that motion is a hidden architecture, 206 separate bones, locked together with joints, levers, and hinges, doing something that most life on Earth has never been able to do. Because the real answer to "what if humans had no bones" isn't a world where people flop around like jelly. It's stranger than that. It's a world that already exists, right now, all around you, just built on a completely different set of rules. Let's start with the part most people never think about. Bone is not the default setting for animal life. It's the exception. For roughly 3 billion years, life on Earth had no skeleton of any kind, rigid or otherwise. The first animals with bodies large enough to move with purpose, jellyfish, worms, sea anemones, solved the structural problem in a completely different way. They used something called a hydrostatic skeleton. Picture a long balloon filled with water. You can't crush it flat because the fluid inside pushes back. Muscles wrapped around that fluid-filled tube squeeze in one direction, and the incompressible liquid inside pushes the whole body to bend, stretch, or shorten. No bones required. No rigid frame at all. Just water, muscle, and pressure, doing the job that your skeleton does for you. That's still how an earthworm moves today. It's still how an octopus arm bends, twists, and grips in 8 different directions at once, something your own arm, hinged and locked by bone, could never do. Marine biologist Jennifer Mather has spent decades studying octopus behavior, and one of the things that fascinates her most is exactly this. An octopus has no internal skeleton anywhere in its body except a small beak. It can squeeze through a gap the width of its own eyeball. And yet it solves puzzles, opens jars, recognizes human faces, and appears to plan ahead, all without a single bone holding it together. Which raises an uncomfortable question. If intelligence like that is possible without bones, why did anything ever bother evolving them? Here's where it gets stranger. Because the hydrostatic method works beautifully, right up until you try to leave the water or get big. And this is where a scientist named J.B.S. Haldane becomes useful. In 1926, Haldane wrote a short, strange, brilliant essay called On Being the Right Size. And in it he laid out a problem that still shapes every animal body on the planet. As a creature grows larger, its volume increases much faster than its surface area. Double an animal's length, and its weight goes up roughly 8-fold, while the strength of its tissues, which depends on cross-sectional area, only goes up about 4-fold. That means bigger bodies need proportionally stronger support just to avoid collapsing under their own weight. A soft, boneless body can only get so big before gravity wins. That's why the largest boneless animals on Earth, giant squid included, live almost entirely underwater, where the surrounding water helps hold their bodies up. Pull a boneless giant onto dry land, and it collapses into its own weight almost instantly. So evolution needed a workaround, and the first attempt wasn't bone at all. It was armor. Around 500 million years ago, early arthropods, the ancestors of insects, crabs, and spiders, developed exoskeletons, hard shells worn on the outside of the body instead of the inside. This solved the size and support problem, up to a point. An exoskeleton is strong, protective, and doesn't require growing a whole new internal structure from scratch. But it comes with a brutal design flaw. It can't grow with you. Every time an arthropod outgrows its shell, it has to shed the entire thing and grow a new one underneath, a process called molting, and during that window the animal is soft, exposed, and almost defenseless. It's also part of why insects and crabs stay relatively small. An exoskeleton that could support something the size of a large dog would have to be so thick and heavy that the animal could barely move under its own weight. The largest arthropod that ever lived, a sea scorpion called Echolopterus, only reached about 8 feet, and it lived entirely supported by water, for exactly the same reason the giant squid needs the ocean. There was actually a stop along the way before true bone showed up, and it's still swimming around today. Sharks and rays never evolved bone at all. Their entire internal skeleton is built from cartilage, the same flexible tissue that shapes the tip of your own nose and the outer curve of your ears. Cartilage is lighter than bone and more flexible, which is part of why sharks can bend their bodies in ways a bony fish can't. But it's also softer, weaker under sustained load, and it doesn't store minerals the way true bone does. That's a real limitation. It's a big part of why sharks stay buoyant with an oversized oily liver instead of relying on a dense internal frame, and why a shark stranded on a beach can suffocate under the crushing weight of its own body within minutes, something a bony animal built for gravity would never experience on land. Cartilage was a genuine improvement over having no internal skeleton at all. It just wasn't the version built for leaving the water behind. Which brings us to the third and, so far, final experiment, the internal skeleton, bone. And this is where the story gets personal, because it's the one that led directly to you. Paleontologist Neil Shubin spent years searching specifically for the fossil that would show this transition happening, and in 2004 his team found it on Ellesmere Island in the Canadian Arctic. It was a fish called Tiktaalik, 375 million years old, with gills and scales like a fish, but also something new, the beginnings of wrist bones inside a fin. Shubin's discovery mattered because it showed, in physical, fossilized form, the exact moment a body plan meant for water started building the internal supports it would eventually need to survive on land. Not armor worn outside the body, but scaffolding built inside it, capable of growing continuously, without ever needing to be shed. An internal skeleton solves nearly every problem the other two options ran into. Because it grows with the animal instead of trapping it inside a fixed shell, there's no size ceiling forcing a return to the water. Because the framework sits inside soft tissue instead of outside it, muscles get far more efficient leverage, letting a bone-based body move faster and use less energy than either a hydrostatic or exoskeletal one of the same size. And because that framework is rigid and load-bearing rather than fluid and pressure-dependent, animals with internal skeletons were finally able to walk, run, and stand upright on dry land without collapsing under their own mass. Every large land animal alive today, elephants, horses, exists because that transition happened. Without it, nothing above a certain size ever leaves the water at all. But bone did something else too, something that has nothing to do with movement. It became a mineral bank. Roughly 99% of the calcium in your body is stored inside your bones, along with most of your phosphorus, released into your bloodstream whenever your body needs it for something else entirely, like signaling between nerve cells or contracting a heart muscle. Your bones are also where your blood is made. Deep inside certain bones sits soft tissue called bone marrow, and that marrow produces roughly 200 billion new blood cells every single day. An octopus doesn't have that internal factory. Neither does an earthworm. They solve the problem of survival differently, sometimes brilliantly, but they solve it without ever building a mineral reservoir or a blood cell nursery into their own structural support. So picture it now, a version of you with no bones anywhere in your body, not a wobbly version of yourself standing upright and jiggling. That image is actually the wrong one, and it's worth sitting with why. Without bone, you would have no rigid points for muscles to pull against, which means no standing, no walking, no lifting your own head off the ground for more than a few seconds. Your body would have to rely on a hydrostatic system instead, water pressure and muscle, the same basic engineering an earthworm uses. Following Haldane's math, that system caps out fast. A human-sized body built entirely on hydrostatic pressure could not support itself on land at all. It would need to stay in water, most likely a slow, boneless, tube-shaped creature the size and shape of something between a jellyfish and a very large slug, moving by contracting muscles in waves, the way a sea cucumber does today. There would be no walking upright to free your hands. No hands to free, really, not in any grasping, dexterous sense, not without joints for fingers to bend at. No skull to protect a brain, which means no safe place to evolve one much larger than what you'd need for basic reflexes, because an unprotected brain is a fragile, dangerous thing to carry around. No hips to give birth through, no ribs to protect a heart and lungs from every minor impact, no jaw to chew solid food efficiently, which would push your entire diet back toward the soft, low-energy foods that don't demand cutting or grinding. And here's the twist that actually reframes the whole question. The reason an octopus gets away with having no bones isn't that it found a workaround to the problems bone solves. It's that it stopped needing most of those problems solved in the first place. It never left water, so it never needed load-bearing legs. It grows a new beak instead of storing minerals in an internal skeleton. It relies on a decentralized nervous system, with more neurons in its arms than its brain, instead of one large protected organ making every decision. Every single trade-off you'd expect a boneless human to make, the octopus already made, generations ago, just in a completely different direction. Boneless intelligence is possible. It's just built for a completely different kind of life than the one you're living right now. Typing, walking, standing at a kitchen counter making coffee with a spine holding your whole upper body upright without you ever thinking about it. Which is really the point. Bone isn't just what holds you together. It's the specific set of trade-offs that made your particular kind of life possible. Land instead of water, upright instead of crawling, a protected brain that could afford to grow large, hands precise enough to build things smaller than themselves. Take bone away, and you don't just lose your shape. You lose the entire chain of decisions your body made over hundreds of millions of years about what kind of creature was worth becoming. You reach up and scratch the back of your neck, your wrist bends, your fingers curl, it still feels like nothing. Now you know it's actually the end product of 3 different evolutionary experiments, one of which had to work well enough to get you standing upright, thinking, and reaching for the back of your own neck without a second thought.